All right, we're continuing the idea that we established in the last set of notes that physical and chemical properties of substances depend on their bonds and or their intermolecular forces, and we're going to just make sure that we establish that a little more thoroughly. Okay, it says here physical properties. So we already kind of established this, but let's make sure we get it down. Physical properties of molecular compounds depend on the strength of their intermolecular forces. So we could say IMFs, or we could say inter. Make sure that we spell that right, inter, not intramolecular forces. The physical properties of ionic compounds depend on the strength of their ionic bonds. So the physical properties for a molecular compound depends on the attraction between molecules. The physical properties of ionic compounds depends on the strength of the bond between ions or within the ionic compound. So a key point, strong IMFs or strong ionic bonds mean that you're going to have a high melting point, high boiling point, and a low vapor pressure. We haven't really talked about vapor pressure yet, but you notice this is the opposite. Weak IMFs or weak ionic bonds lead to a low melting point, low boiling point, and a high vaporization pressure. Again, you see that that's the opposite. Okay, let's establish what each of these mean. Melting point, you know, is the temperature when a solid turns into liquid. The boiling point is the temperature when a liquid turns into a gas. By the way, the melting point and freezing point are the same. That's one thing to keep in mind. Okay, that temperature will be the same. Vapor pressure. Vapor pressure at a particular temperature is the pressure exerted by a vapor, which means gas, in equilibrium with its condensed phases, solid or liquid at a given temperature in a closed system. What that means is the amount of pressure that the gas is making trying to escape out of the container. So if you have strong intermolecular forces, the gas is going to try to, there's not going to be much gas trying to escape from the substance. The tendency to change into a gas and to create that pressure is very low. But if you have weak intermolecular forces, the vapor pressure will be higher because there's not as much attraction holding those molecules together, so it's more likely for one of them to get away and to turn into a gas. We want to continue with that idea. Chemical properties of molecular compounds depend on the strength of their covalent bonds. Where chemical properties, and again these are chemical, not physical properties of ionic compounds now, depend on the strength of their ionic bonds. So strong covalent bonds or strong ionic bonds will lead to low reactivity. This was supposed to be an arrow, but it showed up differently in my notes and possibly in yours. So those should be arrows. But a strong covalent bond or strong ionic bond leads to low reactivity, and a weak covalent bond or a weak ionic bond leads to high reactivity. It's because those bonds are harder to break if they're strong, they're easier to break if they're weak, and if they're easier to break, they're more likely to be involved in a chemical reaction where bonds are broken and then formed. So looking at an example problem, it asks us to observe the data table above and explain the molecular interaction and its strength for water and ethanol. So really what it's asking us to do here is look at the boiling points, and you see that they're different. Look at the vapor pressures, you see that they're different. Let's see if we can explain why based on their molecular interactions. So just looking at the data table, we can make some predictions about their molecular interactions or their intermolecular forces without actually even knowing anything about water or ethanol. We know that the boiling point of water is higher than the boiling point of ethanol. From the data table, we know that. And we know that the vapor pressure, so we can just, let's abbreviate that VP of water, is less than the vapor pressure of ethanol. What that tells me, something about their intermolecular forces. So what that means is it means therefore, so that's that 3 dots means therefore, the IMFs for H2O must be stronger than the IMFs in ethanol. And that's a sufficient explanation based on the information given. We just look at the data table and say boiling point's higher for water, vapor pressure is lower for water, therefore the intermolecular forces for water must be stronger than intermolecular forces in ethanol. In combustion with air, so combustion, that's a chemical reaction or a chemical change. It says oxygen gas reacts with the compound combusted, but nitrogen gas doesn't. Okay, so that means this is unreactive. So why would oxygen be more reactive? It wants us to explain that phenomenon. So in order to really explain that, we've got to look at the strength of the bonds. Okay, not intermolecular forces, but because we're talking about a chemical change, we need to compare the strength of chemical bonds. The way we're going to do that is by drawing the structures. So let's do that really quickly. Oxygen gas is O2. O2 has 6 times 2, that would be 12 valence electrons. So if I'm drawing a bond, if I'm drawing the bond for oxygen, it's going to look like that, and I've used 2 of my electrons, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so I've got one oxygen atom that has 8 around it. The other one has 6 valence electrons around it. This oxygen on the right is not very happy, so I'm going to need to take those 2 electrons and move them down there to form a covalent bond. So let me erase these, and we're going to turn those into a double bond. Okay, so we have a double bond. Let's draw nitrogen now. Nitrogen is N2, which has 5 valence electrons times 2. That's 10 valence electrons. So N, that's 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, neither nitrogen has the number of electrons at once, so this one will share a pair. That would get the one on the right a total of 8 valence electrons, but the one on the left would still have only 6. So we actually need to share this pair of electrons as well, which would end up giving us a triple bond. It would look like this. Again, that's a triple bond. Okay, and so why is it that nitrogen doesn't react but oxygen does? Well, oxygen is more reactive because nitrogen has a triple bond, which is a stronger bond. Nitrogen has a stronger bond, so it is less reactive. Oxygen has a weaker bond, compared to nitrogen because it's a double bond instead of a triple bond, and that makes it more reactive.